This is the second of 3 lessons on the Gyro Magnetic Compass. In the last lesson, we established the need for the Gyro Magnetic Compass, and we showed the basic components which make up the system. We said that the purpose of the detector unit, or flux valve, is to sense the Earth's magnetic field and reproduce it within the compass indicator. The detector unit is positioned in a part of the aircraft least affected by onboard electrical fields. This is usually the wingtip or tail fin, where any aircraft-generated magnetic disturbances are at a minimum. This is a typical detector unit. The circular plate is screwed to the underside of the wing. The black hemisphere protrudes out into the airflow and is simply a protective cover for the flux valve inside. The cable carrying the signals passes along inside the structure of the wing. The primary component is the flux valve, a 3-spoke device, shown in red here to make the spokes obvious. In fact, they are a silvery metal colour. The 3 spokes on their own look like this. The flux valve is pendulously mounted on a device known as a Hooke's joint, which enables the detector to swing within limits of 25 degrees about the pitch and roll axes. This is to allow the flux valve to hang level, even if the aircraft pitches and banks up to 25 degrees. However, the Hooke's joint allows no rotation in azimuth. This is because the flux valve must follow the direction of the aircraft's heading. The curved ram's horns at the end of each of the 3 legs are simply to improve magnetic flux gathering efficiency, but they do not affect the principle. The flux valve would detect the Earth's magnetic field even without them. To explain how the flux valve works, we will start by considering just a single leg, without the curved part on the end. Alternating current is fed to the coil wound around the centre post, which in turn produces fields of opposite sign in the top and bottom legs of the flux valve. The magnetic flux, which is a measure of the density of the lines of force in legs A and B, is shown here as red and blue lines. They are at the same frequency and amplitude, but are in antiphase. Note that the pick-off coil is wound around both of the legs A and B, and so their effect will be added. If we add the components A and B together, the resultant flux, which is shown here by a green line, is therefore 0, and so no current is induced in the pick-off coil. So far, we have been looking at the coil in isolation, without considering the Earth's magnetic field. However, if the flux produced by the Earth's magnetic field were present as a background, the positive and negative flux would start from a different baseline, which would not be 0. Therefore, they will be shifted up like this. But the physical characteristics of the metal used in the flux valve legs are such that it magnetically saturates at a certain level. The metal will not magnetize further beyond this. This causes the curve to top out at a limiting saturation level, giving the flattened response shown here. Now when we add the total flux from both legs, A and B, together, the resultant follows the path of the green line. The operation of the flux valve is in accordance with Faraday's law of electromagnetic induction, which states that if the number of lines of force threading a circuit is changing, an induced electromotive force will be set up in the circuit, the magnitude of the EMF being proportional to the rate of change in the number of lines of force threading the circuit. So the secondary winding, the one coloured red here, will pick up change in magnetic flux density, that is, the dips in the green line, as an EMF. This will be detected as an AC signal. Therefore, if our coil round the legs of our flux valve spoke is pointing northwards, it is in line with the Earth's magnetic field and will pick up an EMF. However, if it were pointing eastwards, it would be pointing at 90 degrees to the Earth's magnetic field and would not detect anything. So the voltage from the flux valve spoke depends on the direction of the spoke relative to the Earth's magnetic field. It is a function of the cosine of the magnetic heading. Unfortunately, we cannot simply measure the voltage and work out our heading, because, except for 0 and 180 degrees, there are two possible values of heading for each value of voltage. Also, if there were any slight change of input voltage, it would give an altered value of output voltage, resulting in a different measured heading. Instead, we use 3 spokes in the flux valve, and the output from each leg is fed to one of the 3 coils, which are situated around the direct drive shaft in the compass indicator. These coils are called stators. Each spoke of the flux valve senses a different voltage, because they are spaced 120 degrees apart, and therefore make a different angle to the Earth's magnetic field. These 3 different voltages are passed to the respective legs of the stator. This creates an AC field in the direction of the aircraft's heading around the direct drive shaft. We now have to detect this. We do this by inserting a device called a rotor into the centre of the stators. It is a wound coil mounted on the gyro drive shaft. If the coil is in line with the AC field generated by the stators, a secondary AC voltage will be induced in the rotor. However, if the rotor is at 90 degrees to the AC field, no secondary voltage is induced. This is known as the null position. At any position other than the null, some secondary voltage is induced. This is the error signal which we covered in the first lesson. These are not complicated ideas, but this is quite a lengthy sequence, so if you want to go through it again, click on the Replay Scene button. This secondary induced voltage is passed to the precession amplifier, where it is amplified, phase detected, and rectified to DC. The reason for the amplification is fairly obvious, that the unamplified error signal is not powerful enough to drive the precession motor. The purpose of phase detection is to detect the sense of the error. It is important that the precession motor knows which way to turn. Suppose that the gyro shaft is misaligned 2 degrees clockwise from the null. The motor should rotate the shaft 2 degrees anti-clockwise, not all the way round 358 degrees clockwise. Otherwise, the system will go into continuous rotation. Finally, it has to be rectified. This is because the mechanism of the precession motor is a DC torque motor. Therefore, a change in polarity causes a reversal of rotation. The error signal continuously drives the precession motor at the slow precession rate of around 3 degrees a minute, until the rotor reaches the null position with respect to the stators. Let's summarize what we've covered in this lesson. The magnetic detector unit is positioned in a part of the aircraft least affected by onboard electrical fields. This is usually the wingtip or tail fin, where any aircraft-generated magnetic disturbances are at a minimum. The primary component is the flux valve, a 3-spoke device. The flux valve is pendulously mounted on a device known as a Hooke's joint, which enables it to hang level even if the aircraft pitches and banks up to 25 degrees. However, the Hooke's joint allows no rotation in azimuth. This is because the flux valve must follow the direction of the aircraft's heading. We showed that the output of a single spoke of the flux valve is a function of the cosine of the magnetic heading. But, because of ambiguity, we use 3 spokes in the flux valve, and the output from each leg is fed to one of 3 stators. This creates an AC field in the stators around the direct drive shaft. A rotor is mounted on the gyro drive shaft. If the coil is not at 90 degrees to the AC field generated by the stators, an error signal drives the rotor to the null position. The error signal has to be amplified, phase detected, and rectified to DC. The error signal continuously drives the precession motor at the slow precession rate of around 3 degrees a minute, until the rotor reaches the null position with respect to the stators. This concludes the lesson on the flux valve. The next one will look at the remaining components of the Gyro Magnetic Compass, and also how magnetic heading is transmitted to other instruments.